Hello everyone, welcome back to Labtube. In this video I'm going to do question 1 from section 16.4 in which we are asked to evaluate the line integral of a vector field in two ways. One, directly using the definition, and two, using Green's theorem. So this is now the line integral and that's the curve. To do this question, I have to recall you guys two things. First, what is the direct method of evaluating a line integral for vector fields? If you have f dr on any curve, or like this, sometimes it is written by p dx plus q dy. Same thing written in two ways. It is going to be given by this. If you find a parametrization for C using R, then you're going to have evaluate your parametrization into your vector field. And then find R prime, dot product them. You get a function and then evaluate that regular integral. The second method for this question, which is Green's theorem, says if you have a simple, closed, positively oriented curve, C, then f dr, which is again other way of writing that, is p dx plus q dy. This is going to be equal to a double integral over the region inside the curve, and then dq dx minus dp dy dA. So that's what Green's theorem says. Now, let's see what are the vector fields and curve for us in this question. The vector field, the coefficient for dx is the first component, and it is y squared. And the coefficient for dy is the second component. That's my vector field. And what about the curve? Curve is that rectangle. So I have xy axis, rectangle going from 0, 0 to 5, 0, this one, up to 5, 4, come back to 0, 4, and then go down. That's the curve we are going to integrate our vector field along. So let's do type 1. So using direct definition. For that, I need to parameterize this curve by a vector function. I cannot do that because this is kind of bad curve. It is formed by 4 pieces. And in this case, these were the direction. In this case, I have to separate pieces, and then the line integral on the whole thing is going to be sum of line integral on each piece. So I do this first on C2, on C3, and C4. When you're done, add them. And add them, you get the whole integral. So let's do one by one each piece and then add them. So on C1, I have to find a parametrization for C1. good parameterization for line segments. So parameterization, this is a side note. If you keep in your mind, it will be helpful in all these questions. A parameterization for line segment from a point P to another point Q. This is the easiest and best parameterization you have. RT, you put the initial point, the point you start with, then plus T times Q minus P. And then if you use this parameterization, the values of T, if they varies from 0 to 1, you will cover the whole line segment. I'm going to use this parameterization for all these 4 pieces. C1 is the line segment going from 0, 0 to 5, 0. So our T is 0, 0 minus T times end point minus the initial point. So 5, 0 minus 0, 0. This gives me negative 5t and 0. And again, t goes from 0 to 1. Okay, since I don't have enough space, let me just write the parameterization here. And I know that t goes from 0 to 1. Now I have space for all the integrals. Okay, so then integral over C1 of f dr is going to be go from 0 to 1. Plug in this parameterization into your vector field. So y is 0. I plug in 0, you get 0. And in this guy, I again have 0 dot. R prime, so find partial derivative of this vector function. And dot product them, you get integral of 0. And integral of 0 is 0. That's the first piece. On the line integral along this curve is 0. For C2, the parameterization is, we want to go from 5, 0 to 5, 4. So I have to do 5, and then t times this minus this. There is no t for first component. And 0 plus t times this minus that. It is 4t. And t goes from 0 to 1. Okay, that's the parameterization for C2, going from this to that. And now my line integral along this guy. Write everything in the parameter t, so it goes from 0 to 1. Plug in this into your vector field. So my vector field along this curve with this parameterization would be y squared, which is 4t squared, x squared, 5 squared, times y, which is 4t. That's my f dot. The derivative of the parameterization or the vector function, it is 0 and 4 dt. Okay, let's dot product this dot that 0, this dot this one. So I have 25 times 4, it is 100, times 4, it is 400 t, 0 to 1 dt. And then integral of 400t is 200t squared. Go from 0 to 1. This gives us 200s. So that's the second piece. Integral along C2 is 200s. C3, on the other hand, is the parameterization is 5 minus 5t. So if I plug in 0, I get 5, and then for 1 get that. and y is this. So I'm using this parameterization. Okay? Then you go from t to 1, integral c3 f dr is going to be, write everything in your parameter. So my x is going to be 5 minus 5t, so second component is going to be 5 minus 5t squared times y is 4, and this is 4 squared. Derivative of this, derivative of the parameterization, it is negative 5, 0 dt. And now I can dot product these two vectors. The second piece will disappear because it is going to multiply by 0. The first component, which is 4 squared, I don't need to put brackets there. It is 4 squared, so it is 16 times, 16 times 5. It is going to be negative 5. It is going to be negative 214. Yes, 5, 4, 20 times 4, negative 80. Sorry. Yes. And then dt. And integral of negative 80 is negative 8t times t go from 0 to 1. It is going to be minus or negative 80. Okay. Integral along C3 is equal to negative 80, and then C4, the parameterization is 0, 4 minus 40. Again, t is between 0 and 1. And C4 f dr is going to be 0 to 1. Plugging this into your vector field, x is 0, so this part would be 0, and y is negative 4 minus negative 4t, y squared, so the first component is going to be that. That's my f dot to r prime. What is r prime? R prime is here. Find derivative of this, which is 0, negative 4 dt. Dot product. First component to first component 0, second component to second component 0, so I have integral 0 to 1, 0 dt, which is 0. Okay, I integrated my vector field along 4 pieces, and now the line integral on the whole curve is sum of the pieces. So I have 0 plus 200 plus negative 80 plus 0. If you add them, you get 120. So we did evaluate the line integral of this vector field along this rectangle, and that's the value we found, 120. Okay, that's part A. Let's do part B. Okay, I have to raise this to open space for my next computations. Okay. Don't need this one. Okay, I'm supposed to use Green's theorem. What is Green's theorem? Green's theorem says that if you have nice curve, what is the definition for nice curve? It is a simple, closed, and positively oriented curve. In our case, it is closed. That's a good part. Simple means the curve doesn't intersect itself unless at the end point. So it doesn't intersect itself. That's simple. And positively oriented means if you move along the direction then the region inside the curve, in this case is this, should always stay in your left. So if I move along this, this is my left, 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 left. So that's positively oriented. Then in that case, also you need to know what is the region inside the curve. In this case, it is all xy such that x is between 0 and 5 and y is between 0 and 4. So I have D, and with this kind of vector curves, if you have line integral of a vector field, or in our case, I have y squared dx plus x squared y dy. This is going to be equal double integral over the region inside the curve of this integral. Q, find partial derivative of q with respect to x. So it is 2xy minus p, find partial derivative of p with respect to y. It is 2y. Then d. It is a double integral. Now, to evaluate double integral, I have to make it into an iterated integral. So, iterated integral, it is a rectangular region. That means the best thing would be make it into Cartesian coordinate iterated integral. I'm going to make it into the Cartesian iterated, and then I have 2x y minus 2y. The inner one is x, the outer one is y. Now I have an iterated integral. I have to do the inner one first. So the inner one is antiderivative of 2xy minus 2y with respect to x. It is x squared y minus 2xy go from 0 to 5 dy. Okay, let me compute this. You plug in 5 there. So I have 5 squared 25 minus of 2 times 5, 10. 25y minus 10, 5. It is 15y dy. Okay. Now, I have integral of 15y. It is going to be 15 over 2y squared, go from 0 to 4. And plug in values. So it is 15 over 2 times 4 squared minus 15 over 2 minus times 0 squared. And if you do that, you get 16 over 2, it is 15 times 8. 15 times 4 is 60, and 2 of them, it is 120. So we did use Green's theorem, and we changed our line integral to a double integral, and then iterated one and evaluated. And note that because we are evaluating the same integral, the values are same. And that's kind of a confirmation for Green's theorem. That was it. Have a great day, and thank you for watching this video.